Hey everyone, welcome and thank you for coming to my talk. My name is Matt Bajor and I'm an infrastructure automation engineer at a company called Rally Software out in Boulder, Colorado. My responsibilities there include development and maintenance of our containerized build system. So we're doing a lot of things with Docker in particular. Over the past, my background is in infrastructure automations and operations, and over the past 10 years, I've been in charge of managing from hundreds to thousands of servers, and it's really been my passion. At Rally, they afford us a large amount of time for hacking on projects that we find to be interesting and or really anything that we want to do. And so over the past year, I've spent most of my hack time as well as a lot of personal free time looking into technology that I believe is the next step in virtualization after containers. And that's what we're here to talk about today. So complexity in our systems it comes in two varieties, right? We have necessary complexity, which are complexity that's due to solving problems that are very hard and very complex within themselves. Now, we also have complexity that is sort of unnecessary. This is driven from a lack of understanding of the problem or perhaps organic growth over time. So let's take a look at today's modern containerized architecture. So we start up here and we have our edge-facing services. We have some dynamic DNS and traffic routing, and that gets its configuration information from our service metadata, our service registries, such as etcd or Zookeeper. We have various types of stores. We have memory stores, such as Redis and Memcached. We have object storage, such as Swift and S3, as well as relational database stores, such as Postgres and MariaDB. And also document DBs, such as CouchDB and Mongo. Now, this is our primary applications running, polyglot applications running on the platform itself. And these are all tied together with orchestration, such as Kubernetes and Mesos. And we control all of this and manage all of this with configuration management, such as Puppet and Ansible and Chef. These systems work for us, but they're extremely complex. They're very hard to reason about as a whole, and debugging is difficult. One of the reasons that makes debugging difficult is it's almost impossible to replicate the environment in which you're running one-to-one. And there are many, many layers of supporting code here. If we dig into our application stack itself, and this is just what would be running our application directly. You can see we start down at the hardware and have hardware drivers and a hypervisor that uses them to segregate our hardware and split it up. And then on top of that, we have our operating system like Ubuntu or CentOS or any other Linux-based service. Now, that uses virtual hardware drivers and the kernel and user processes to keep everything isolated and running. And then on top of that, we add our Docker runtime. Now, within the Docker container, we have the shared libraries that our application needs. We have the language runtime. We have the application itself and the application config. Now, there are many layers of abstraction and isolation in this. It's hard to know how everything's going to interact all the time. There are many upgrade cadences to match. When you need a new functionality up here in your language runtime, there's a lot of upgrade cadences to match. And a large portion of this is redundant. We have isolation here at the hypervisor layer. We have isolation here with user processes. And then we have isolation again within Docker. And this is all to run a single app with a single user on a single server. And this leads to some problems, such as unnecessary complexity problems. Now, from a developer's perspective, there are a lot of black box layers underneath the application that's actually running. And the developers normally are not interacting with these layers explicitly, and so it can seem very much so like a black box. They're used implicitly, but they're not necessarily knowing exactly how it's interacting. And as far as they're concerned, it may as well be turtles all the way down. We also have overgeneralized systems. POSIX is by its nature generalized. It was invented in a time or created in a time in which we were running the same application against a constantly changing set of hardware. Well, now that's not necessarily needed as much. We're more or less running our virtual machines on hypervisors, and we have a handful of virtual device drivers, and that's about it. The systems in the microservice architecture are by design very specific, and so the overgeneralization can become a little bit of a problem. A huge amount of complexity is within the Linux kernel with protection. The kernel's, one of the main jobs of the kernel is to keep the kernel safe from applications and users, to keep users safe from applications safe from users, applications safe from each other, and users safe from each other as well. That's a lot of code and a lot of complexity in the system. And there's also a lot of needless permission checks. Operating system permissions are not only hard, but it's an outdated model from the time-sharing computers of the 50s and 60s, in which you had many applications and many users on the same piece of hardware, all interacting and all having to work with each other and to get a job done while on the same system. It's very hard to get right, and it's time-consuming to reason about and develop. Now, we also have some efficiency and duplication problems as well. We're using a lot of storage and RAM for things that may not be in use. We have various drivers on the system when in reality we're only interfacing with disk and network virtual drivers, but we still have floppy disk drivers kicking around and tape drive drivers and all these other things. We have a lot of, or not a lot, but there may be unconfigured or unstarted services on your system as well. There are services on your system that are running and not necessarily being utilized and just taking up resources. And there are also duplicated services that are running in maybe too many places, such as SSH. If you have a Bastion host that allows you to connect into your REPL, running SSH on all your hosts as well is not necessary. Now, patching and upgrading software is a time-consuming and risky business. Keeping track of all the patches and errata that need to be applied is a very daunting task. And applying patches after hours is not super fun, as any of you know. Patching, in addition, patching is not, at this point in time, broken down normally into functionality versus security. When we go in and patch a system, we're going yum update and applying everything that is there, whether it's security or functionality. And if it's not in use, why are we paying the price for it? And if you look at it in the right light, it looks like maybe our microservice architecture sort of duplicates what Linux is doing for us. We have our configuration here, via service registration, etcd, key value stores. We have our process management going on here with Kubernetes and Mesos. We have our in-memory storage and our disk storage. And then we have our individual worker processes themselves. This sort of duplicates what the Linux system has done for us. And it almost is identical to what we're relying on Linux for at this point in time. Now, there are also a few security problems, and this is just a very short list. I'm sure if you ask your local security engineer, he'll be able to elaborate on this much more in depth than I will. We have a very large attack surface. The kernel itself is a huge code base. With a larger code base, it's easier to find entry points into the system and to get in and compromise the application. In addition, there's a lot of common applications, services, configurations, and libraries that are on our Linux deployments. And security patching is done by a separate team. This is normally done at the operating system level. There are a lot of unknown interactions because each change set we're applying is different size and different shape, and it's going to affect our systems in different ways. And every time we do that update, we don't know exactly how it's going to affect us. This can lead to possible production outages, which we can't handle, or rather we don't want to experience. And it's also problematic because the people who are applying it don't have a full understanding. There's a lack of understanding of the implementation of the code that they're actually upgrading. Now, most of the exploits out there these days do target Linux. A larger user base equals a larger chance of successful attacks. And attacks against the hypervisor are slightly less common. The hypervisor is more secured. It's not necessarily exposed on the internet. And so you see a lot fewer attacks. In order to develop an attack against a hypervisor, normally you need to have a machine on the box, either via managed hosting or AWS or something like that. And in these cases, we've taken precautions in order to negate that and sort of limit the capabilities of these servers. And since everything is so common, an attack on one deployment of Linux can, in theory, be applied to other deployments that are out there as well. And with a Docker-based platform, there's a lot of sharing going on. We're sharing the kernel, we're sharing memory, we're sharing file system, as well as the hardware. And really, the only thing that's keeping us safe are some kernel extensions, such as C groups and stuff like that. We're sort of building a wall of protection. Now, how did we get here? Well, we got here over natural evolution. We've evolved to use different architectures and hardware. We've gone from mainframes to client-server architectures to distributed microservices, and Unix has supported us the entire way. We have decades of backwards compatibility built into Linux that there's no real easy way to remove it. You can't go in and carve out the things that you don't want in an easy way. And I would even wager that at this point in time, you could install the latest Ubuntu distribution on a 10-year-old Pentium 1, and everything would work as expected. What can Linux run on? Anything. What can run on Linux? Anything. It's one of the most compatible operating systems out there, even though we're only running a single app with a single user on virtual hardware. This has developed a culture of compatibility over efficiency, and this is one of the trade-offs that we've made. Now, it allows us to do everything we need to do very easily. We are able to do what we need to do. And part of the reasons why we're able to do that is the great tooling ecosystem. With things like Ansible and AWS and OpenShift and OpenStack, we're able to build these really cool, complex systems. And this has gotten us to where we are today, and we're in a working state. We are able to build and deploy working microservice architectures that solve our problems in a fairly elegant way. We've made it work, and now it's time to make it right. And the next iteration will be focusing on performance and making it fast. And the way we can do that is by simplifying. Fewer lines of code equals fewer bugs and fewer things to reason about. And it gives us a better ability to hold the system within our mind and to think about and solve problems. And that's why I propose that we start thinking about using unikernels. Now, what is a unikernel? A unikernel is a specialized virtual machine that contains your application's compiled in with its configuration, the language runtime, and a set of libraries that interact with the virtual hardware, known as the library operating system. And if we take a look here, we can see this part, we have our application binary, config, and dependencies, and these are sort of packaged up with your languages tools, the normal build tools that you're using now. And then we sort of bundle it with the language runtime and some virtual hardware drivers via a unikernel packaging tool. Now, these tools vary by distribution. With Erlang's Ling, it's the railing tool. With Mirage OS, it's the Mirage tool. And for runtime.js, it's Runtimeify. But these are implementation-specific tools that do this packaging for us. Now, what it looks like is similar to our application stack. Well, rather, it's serving the same functionality. We're still running our app. We still have our hardware drivers, and hypervisor down at the base level, and our application binary up at top. But we've replaced the middle with library OS. Now, this is only the code that is absolutely required. It's your language runtime, your application, and virtual I/O drivers. And this can also be minimized down to a very basic POSIX interface as well. Then we take these unikernels that have, these artifacts have everything they need to interact with the hypervisor and the world around them. And so they can be deployed directly against the lowest virtualization level, which is the hypervisor. They have their own network stack, they have their own virtualized memory presented as hardware, and they're totally self-contained and ideally immutable as well. Normally, if you're going to be persisting state somewhere, you're going to persist it off of these. Now, comparing them directly to a Docker stack, you can see there's a lot less complexity going on here. There are much fewer layers, as you can see, and even though this model accomplishes the same thing, there's significantly less code. There's no permissions, there's no isolation, and there's no unused libraries. Now, within unikernels, there are two types. There are POSIX compliant types, and these are targeted towards backwards compatibility and running your unmodified application in a minimal footprint. They're fairly generalized and more backwards compatible. But they do allow you to run your unmodified application in a unikernel type fashion, and taking advantage of some of the things such as efficiency that you can get from, and size at least. Now, you don't necessarily get all the benefits of decreased complexity, but you do get, you are able to run in a unikernel type architecture without modifying your application. Now, looking forward, we have forward compatible ones, which are more language specific type. And so these are lean, mean, and specialized, and these really take advantage of all the things that unikernels can offer. Now, there's very little backwards compatibility in there, though. So, how can unikernels help address our problems? Well, taking a look at our unnecessary complexity problems, we've removed a significant layer, a lot of layers of complexity. We've removed backwards compatibility and legacy support, and we really only include what we need. And so this makes the system that we're designing significantly more simple. We've also shrunken and specialized our runtimes. Fewer lines of code equals fewer bugs. A smaller code base is easier to reason about, and our mean time to resolution on these priority 1 bugs can go down significantly. Also, because everything is so small and so compact, we can really increase our density and reach much higher densities on our commodity hardware that we're running right now. Now, with no other users in a time-sharing sense, the application can really utilize the system in any way it wants. There's a single process and single memory space, so there's no need for permissions. There's much less complexity in the corresponding library OS to support this. And this doesn't mean that your application itself can't support multiple users. This just means that there's no multiple users in the sense of etc password, which is not really relevant since 2010, where we're not necessarily, or ideally, we're not logging into these machines at all. We're running our application and our application only in an immutable way. Now, we have isolation at the virtual hardware layer. This is the lowest level that we can isolate, other than physical machines, but we don't want to own a fleet of infinite physical machines. Isolation at this level is the simplest and most effective. It's the smallest footprint and smallest area to secure. Now, taking a look at our efficiency problems, a minimal VM, even with nothing on it, say you want to just have a VM, you're still looking at about 1 gigabyte in size. A minimal unikernel is tiny, it's kilobytes in size. And so even with a full unikernel, you're still looking at megabytes in size. And so that means you can go ahead and say we were going to deploy a static site. If we were to deploy a static site on Nginx on Linux, we're going to take up about 1 gig of RAM and about 1 gig of disk. Well, if we were to do that in unikernels, we could run a static site with about 4 megabytes of RAM, and even less disk. Now, our microservice architecture sort of duplicates Linux. Since we have built and maintained these architectures, which are very time-consuming and they take a lot of effort to build, and a lot of effort and time and thought to build and maintain, we should use it as much as we can. We should use it to replace the things that it can replace, and do that as effectively as possible. Now, there's no permissions checks at all, and so you can really eke out every bit of performance out of your hardware. You can run your application in direct kernel CPU mode, and so without any permissions checks anywhere, and you're able to utilize your hardware 100%. And this also raises a curious thing of it removes that layer of abstraction in which you're required, most Linux systems, or rather Linux was developed with the abstraction being in the file. Well, without that abstraction being there, we can go ahead and think about things in new ways. And one thing that I read the other day is that someone, instead of taking things off of the network, writing it to disk as a file, and then reading it back out, they were proposing taking network packets off of the network, stripping off the headers, and writing those to disk. And then when you go to read it, you're reading network packets directly off of the disk. So it gives us a different way of thinking about things if we so choose. Now, when it comes to security problems, we have a very small attack surface now. It's really only our application and the libraries that are required. There's no extraneous software on there, and there's very few shared libraries interacting. And almost every deployment is completely different. So even if you're able to get into one deployment, that attack is not going to work on another deployment down the internet. There's no real common entry point either. Each deployment is very unique. And the other thing is that once unikernel is compromised, there's really very little you can do. Since there's no software other than what is required to run your application, there's no shell, there's no compiler. You don't have any access to the memory around you. You have only what's in your application's memory. So we're no longer in the realm of script kiddies sort of scanning IPs, finding a compromised WordPress, and installing an egg drop bot. Now you're looking at professional hackers getting in, and even once they get in, they really only have access to the memory of the service, memory encode of the service that they've compromised. Now, this may not hold true forever. As unikernels grow in popularity, there may be attacks that target the library OSs and whatnot, but it is still much more specialized and much more unique than a standard Linux install. And we can also have dev teams manage their own patching. The team that wrote it runs it. The team that implemented the software is fully able to reason about the impact of an upgrade to a library or some other piece of software within their system. And the ownership of the entire runtime is within their hands. And so when they're developing and hit a bug or a problem that is unfamiliar to them, there's no chance that it's related to the production runtime environment or something outside of their code base. It's only using the code that they have explicitly included. And so when they reach a problem like that, they can know that the problem is with the code that they're writing. And essentially, the only thing that is shared is the hardware. Ideally, you're running a Type 1 hypervisor, and the only real commonality is the hardware between unikernels. Now, there is a shared kernel in the sense that Zen itself is a kernel, but the applications are not interacting with it in the same way that they would be with a standard Linux kernel. It's providing the segregation of hardware for them, but nothing else. Now, this doesn't always hold true, as we don't always run Type 1 hypervisors. But still, even if you're running a Type 2 hypervisor, such as KVM or Zen on top of Ubuntu, and sorry, let me back up. We split up hypervisors in two ways. Type 1 is a hypervisor that runs on the hardware itself. There's no operating system other than the hypervisor itself. Type 2 would be something like KVM, who runs within the Linux user space and provides virtualization in that way. So if you're running it as Type 2, you do still have a Linux system underneath, but it is as low as you're going to get in the stack without running a Type 1 hypervisor. Now, there are quite a few projects out there in the wild, and we're going to go over a couple of them here. But if you don't see one that looks super interesting to you, Google unikernel in the language of your choice, and I expect you'll be able to find something that you find interesting and useful and are able to play with. The first one we're going to talk about here is Mirage OS. Mirage OS is a language-specific unikernel that utilizes the OCaml language. It's developed by the University of Cambridge and is released under the MIT license. It supports both Zen and Unix as a runtime. And the reason why they support Unix is so that you're able to go ahead and develop and iterate within Unix, running your unikernel in Linux user space. And then once you're ready, go ahead and package that up and seal it and ship it out as a production-ready unikernel. So it gives you fast development iterations while still being able to utilize unikernels. So you're not building this thing every 5 minutes. It supports both x86 architectures and ARM. And so that's very interesting. You're able to run these on any type of ARM-based device as well as standard x86 hardware, which is very cool. The next one is rumprun. Rumprun is a POSIX-compliant unikernel. It's written in C and developed by the NetBSD community. It's licensed under BSD, but as these things go, if you include various libraries, they may have different licenses as well. It supports x86 and ARM as well, and this is the first implementation of NetBSD's any kernel concept. The NetBSD any kernel is a version of the BSD kernel that they've modified to make modular. And so you're able to take pieces from here and pieces from there and put them together and use what you need from that kernel while not including the whole thing. And this has gone through a lot of work in order for them to make it like that. The next one we're going to talk about is runtime.js. This is a language-specific unikernel that's based on the JavaScript V8 engine. This is developed primarily by the open source community, and it's licensed under Apache v2. The supported runtimes are KVM, and the architecture is pretty much x86. Now, if you're just beginning to play with these, this is a very good place to start. You're able to use NPM and Node and the tools that a lot of us are familiar with in order to begin developing and running sites within unikernels without having to pick up Haskell or Erlang or OCaml. Although with this crowd, I expect we all like those a little bit better. Another one is Ling. This is also known as Erlang on Zen, and they also have another project called Project L, which is a type-safe version of the Beam implementation. So this uses Erlang. It's developed by CloudDozer LLP. It's under a commercial license, a Sleepycat type license, and it runs on Zen and it supports the x86 architecture. The next one is the HAL VM. It's the Haskell Lightweight VM. This is promoted as a simple platform for simple platforms. It's language specific, and the language it targets is Haskell. It's developed by Galois, and there are a few guys here today from them, and they're a very cool group of people, and they'd happily be able to talk to you a little bit more in depth about this. But it's licensed under the BSD 3 clause. It supports Zen as well as x86, and it's a very cool project. This is what the workshop yesterday was based off of. Now, here's one that you might not expect. This is Microsoft Drawbridge. This is a research project by Microsoft that combines lightweight Pico processes with a Microsoft or Windows library OS in order to accomplish a same unikernel type goal. Unfortunately, this is just an internal research project, and I've had a very hard time finding any code available for this online in order to play with it or to try it at all. But it is very interesting that Microsoft is looking at this. One of the most popular ones out there at this point in time is OSV. This is a POSIX-compliant unikernel. It's in C, and it's developed by Cloudius Systems. It's under the BSD license, but they also offer commercial support, and some are commercial licensed. They have some implementations that are commercially licensed. Now, what's really interesting is that this will support running in unmodified JVM as well as a lot of other unmodified applications. And the other very interesting thing is they don't target just KVM and Zen. They also target VMware and VirtualBox, meaning that you can run these on a Windows-based VMware cluster. They focus on performance, and they actually have just released a product which is a database based on unikernels, which is a Cassandra-type or Cassandra-compatible data store called ScyllaDB, which seems to be very interesting. Another one that we have here is Clive. Clive is a language-specific library OS that targets the Golang language. It's developed at the Universidad Rey Juan Carlos of Madrid in Spain, and it's under the MIT license. They target primarily hardware, and they run on x86 architectures. There's not a ton of information out there, but it does seem to be a very promising product that would allow you to run your Go-based application as a unikernel. And the final one we're going to talk about here is NEC's ClickOS. This is a language-specific unikernel that's built for primarily networking applications. It's in C++ and developed by NEC Labs. Now, it's under an MIT license, but it does have a clause that requires you to get written permission before using NEC's name publicly. It supports Xen and KVM and the x86 architecture. And as I mentioned, this really targets specifically networking hardware and networking gear, such as software-defined networking and other embedded network-type systems. And so that's what I have here for the presentation. Now, in lieu of doing a live demo, which everyone does find interesting and awing, I've created a demo that you guys can all do yourself. And so at this address here, at this GitHub repo, you'll find a Vagrant repository, or rather a GitHub repository that has a Vagrant box as well as a few directories in it. Now, if you do a Vagrant up, this machine will work on either Windows or Linux or Mac, either VMware or VirtualBox, and it will allow you to go ahead and try and build and run these unikernels. And so the first example in there is a Mirage OS example. It will allow you to build a static website with Mirage and go ahead and deploy it against the Xen hypervisor and see what is deployed. In addition, it includes Jitsu. Jitsu is just-in-time unikernel summoning, and so the way it works is that you'll go ahead and fire up this Jitsu daemon, which listens on port 53 UDP and acts as a DNS server and a forwarding proxy as well. And the way it works is when a DNS request comes in, Jitsu will check the hypervisor, see if the unikernel that is there to serve the request is running. If it is, it will go ahead and return your A record. If it is not, Jitsu will go ahead and deploy that unikernel, then return your response, and you're able to access the page. So while there's no traffic on it, there's nothing running whatsoever other than the DNS daemon. Now, this isn't super practical, but it is very cool, and it is something that you may find interesting to play with. The other project, another one that's in there, is a Ling-based unikernel, which is written in Erlang. It's a generic or very, very basic Erlang OTP application that serves a static website. And you can go ahead and compile that down with Rebar, which is included, package it with Railing, and run that against the Xen hypervisor as well. There's also an example of runtime.js and the rump kernel as well, the rump run. Now, the rump one is a little bit more complex, and it might be something that's a little bit more useful for you to play with. It's actually a full WordPress stack. It includes one unikernel serving MySQL, one unikernel running PHP in fast CGI mode, and then a front unikernel running Nginx. And it's a full stack. You're able to go ahead, build these unikernels, spin them up, and install WordPress on them. And so I really encourage you all to go ahead and clone this repo, do a Vagrant up, and start playing with this and build some cool stuff. These unikernels are being used in production, and there are production things out there, so they are ready to start playing with, and I assure you, you will not be wasting your time or your interest looking into this stuff. And that's all I have for you today, and I appreciate you all for coming out. Thank you.